All right, so in your textbook, this is in Chapter 2. It's in sections 8 and 9. Your author actually covers this before he covers sets. I'm not sure why, because it's built from sets. And it actually also is in section 13 as well, although we're not actually going to go over section 13. So if you want to read that on your own, definitely go for it. If you don't want to worry about it, that's okay too. That's section 13. So let us jump to the next slide. And I need to get my keyboard initialized. Apparently, it decided to shut off on me. All right. Okay. We can do this a different way. There we go. All right. So background information that you need is something from sets. Well, sequences too. So first thing that we're going to do is one of the things that your book talks about is he talks about lists. And that actually, I have to admit, is not something you always see in this section on counting, but it's actually a pretty ingenious way of talking about what we're about to do, okay? So we've talked about lists before. They are simply finite sequences. So if you did this without the terminology of sequences, a list is simply what? You put a bunch of objects in a row, and the order in which you place those objects in a row matters. So you have thing 1, then you have object 2, and object 3 to go back to the word object. Okay? Now, one of the things you care about in your list, specifically a finite sequence, so let me actually write this to the end here. We are typically dealing with finite sequences, is we care about the length of that list, or the length of that finite sequence. And that, just like cardinality of set, is talking about the number of objects involved. Okay. Now, in terms of how we deal with length, how we're going to deal with length is we're going to say, all right, we want to build some of these lists with certain specifications, and we need the length to be X long. Okay. Now, we've actually done things like this before, even before our class. So one of the things is talking about ordered pairs. So just to make sure we're comfortable with the terminology, these are, if you've ever played with the XY coordinate plane, which I'm assuming all of you have, your X coordinate, your Y coordinate, and remember what happens with the ordered pairs. What in the what? Just a second. We will start again. I think my hand accidentally got on something there. There we go. So what do we know about ordered pairs here? If you try to write it in the opposite order, as long as those two elements A and B are not the same thing, if you reverse the order right there, your ordered pair is going to be different. So think about in the XY coordinate plane, which is something that we don't normally play in this class. If you had something like 1, 2, you plot that point, that's different than the point 2, 1. Now you can do the same thing with any length list. This is a list of length 2 because there's only 2 objects. You can also have something called an ordered triple, and if you've done anything in 3 dimensions, these would be the coordinates of points in 3 dimensions. If you haven't, don't worry about it. And then you can do this for any length thing you want, and the general term is something called an n-tuple. The n here tells you the length, and the tuple is just the word that's used. So it looks like an ordered pair, except there's n little coordinates in here, or this is a finite sequence of length n. Okay? So that's some of the background. Now, in terms of what we're going to care about, we actually said this just a second ago, we want to count these number of lists, and then there's going to be some sort of criteria attached to them. Okay? That way we know how to build the list. Okay? So that's literally what we're going to be doing, okay, this entire time. So let's actually look at an example. So suppose you have this example, and this example says, hey, we want to know how many ordered pairs we have, where the first object in that ordered pair can only be selected from the integers 1 through 4, and the second object in that ordered pair can only be selected from the integers 1 through 2. Okay? Now, at the end of the day, the answer to this is going to be how many ordered pairs we have. However, before we even start talking about how many ordered pairs we have, for this example, let's actually build out all of those ordered pairs so you get an idea of where we're going, and then we're going to build up to the strategy of how to count them. Okay? In the future, it's often too many of these lists or in this case, ordered pairs, for us to actually write them all out. So we will be focused on the how many of them exist, not which ones they are. Okay? But if we actually did write out all of these guys, what would we do? Well, first of all, formatting. If you have an ordered pair, it would look like that. And what do we know? We're told that the first position can be the numbers 1 through 4, and we're told that the second position can be the numbers 0 through 2. Okay? So if we do this strategically, and let me actually title this for us, ordered pairs. Maybe you start off and pick the 1 to go in that first position, but then who could go in the second position? What do you guys think? Who could we write in that second position? In other words, if we want to finish off this ordered pair, what should I write after the comma? And yes, that is a question for you guys. Yep, you could totally do 0 would be an option. Now, is that the only option? The answer is no. What's another thing you could have put after that comma? Yeah, you could totally have put 1. Now, is that the only option? What in the world? Just a second. All right. It looks like I have a key on my keyboard that gets stuck on me. Now, is this second ordered pair the only option? Again, the answer is no, there should be one more. So what would be that last ordered pair that we could build that starts with a 1? You got it. So this could be 1, 2. Now, are those all of the ordered pairs that start with 1? And I alluded to the answer being yes, but what do you guys think? Could we actually write any other ordered pairs that are different than the 3 we just wrote that still start with a number 1? Yep, so no other options. Why? Because that second slot can only be 0, 1, or 2, so we've only got 3 options to put in, so then we stop. There's no other ways to use the number 1. So if we're going to do this strategically, maybe we then, for our first position, we then move on to the number 2. So for the number 2, what can I put in that second slot? Yeah, we could put either 0 or we could put 2. Could we put anything else in that second slot? Yep. And we could also put 1 in that second slot. So that takes care of all of the options for 2. Now, that takes care of 1 and 2. Could we start with a 3? Well, we're told we're supposed to be able to. So what could we do if we're dealing with 3? Don't overthink this one. We could do the exact same thing we've been doing, except now it's 3, 0, 3, 1, and 3, 2. And are those all of the ordered pairs that we can build? Or is there somebody we've missed? So there is somebody we've missed, at least one of them. What are the 1 or 1s that we've missed? What are the ordered pair or ordered pairs that we've missed? Yeah, it's all the ones that start with a 4 because we missed out on that guy. So pattern-wise, they look exactly the same. So this would be 4, 0, 4, 1, and 4, 2. No lies, it is quite frequent if you actually need to write out all of the different lists of however they've been built from wherever they've been built. This is something that often gets computer generated, okay, or can be computer generated, relatively straightforward. Just because it can be tedious. This is a relatively small example, so it can write it all out just fine, but they get really big really fast. Now, we actually, according to that question, we didn't necessarily care about what all the different ordered pairs were. What did we care about? We cared about how many ordered pairs we ended up with. So let's actually answer the question here. How many different ordered pairs meet the two criteria we were given? Yeah, and how did you find that? So the answer here is 12. There are two ways to find that answer. One of them is to do what? Any guesses? Well, you guys actually jumped to my second way, but yeah, we're going to do that way in just a second. So yep, exactly. So if you write out all the ordered pairs, one of the ways to do it is just count them up, okay? So that's the advantage of writing out all of your different lists, is you can literally just count them up. However, as several of you guys have mentioned, there's definitely a quicker way of finding that answer of 12, and let me show you a classic way of doing it, okay? So this is now sort of a way to answer this question. Here's what you've got. You've got 2 slots for the ordered pair. In the first slot, you have what? You have the options of 1, 2, 3, and 4. And in the second slot, you have the options of 1, 2, and 3. Now, what does this tell you? And I strategically here actually wrote these guys out as sort of a rectangular block so it'd be easier to see. But what happens in the first slot, you have a grand total of 4 choices. And in the second slot, you have a grand total of 3 choices. When you multiply that together, that's where you get your 12. Now, this example was strategically chosen because it's easy to see the tie-in to something we did in sets. Anybody notice something about this particular example that looks really, really similar to something that we did way back when we were working on sets? Anybody notice that tie-in? It's actually, we built a special type of set right here, is what I'm referring to. Anybody remember what that special type of set was? It's okay if you don't, but this is a nice tie-in with something we already know if you do. Ooh, you're close. It's something we did right next to the power set. It's called something else, though. So this guy is actually called a cross product or a Cartesian product. Now this is A cross B, where A equals that first set, 1 through 4, and B equaled the second set, 0, 1, and 2. Now, did anybody remember the cardinality of a cross product? That was one of those activities we did in class a way long time back. Anybody happen to remember how to calculate the cardinality of a cross product? Now I can't tell if the blanks are you guys typing or you're not sure, but this was the rule. You just multiply the cardinalities of the two individual sets. Now, why would I say that is a tie-in to what we just did? Anybody see any comparison between that information about the cross products and what we just did? Don't overthink it. What did we find? We found that the collection of all the lists was the same as a cross product. So the part that we haven't talked about yet is the actual answer, that 12. Why would I say that there may be a tie-in with that 12 with respect to the cross product stuff? It actually relates to exactly what you guys typed in just a little while ago. Yeah, it refers to that multiplication. So here with our cross product, right here, what happened? We said that the total number of elements in our cross product, so with the counting, the total number of ordered pairs was going to be exactly the same as just multiplying the two cardinalities, or in terms of what we have, multiplying the number of objects that could be in set 1 by the number of objects that could be in set 2. So it turns out this thing of building list is really behind the scenes just building a bunch of different cross products. What does that mean? That means you can figure out exactly how many objects could go in each one of your slots. And once you figure out the number of objects in each slot, we're actually going to use this property of cross products where you just multiply those number of objects together to get the final count on the total list that used everything together. Okay? So that's the tie-in. That's the stuff that we've already done. Now, to be fair, we didn't play around with cross products that much, but why we talked about them before was because we were foreshadowing to get to today. Okay? Now, let's put that together in an actual property. So it's something called the multiplication principle, and it's exactly what we just talked about with cross products. Okay? So if you look at list of length n, or formally n tuples, then the number of those lists is given by some product. So this k1 times k2 dot 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 times kn, and each of those k's, so k1 is the total number of objects that the first position in the list could be chosen from. This k2 is the total number of objects that the second the second thing in the list can be selected from. You keep going, and the nth or the last object in your list could be selected from a grand total of k minus n objects from wherever it's being pulled from. Okay? Notice what this is, and let me go ahead and tack this on down here for your list of length n. So list of length n refers to a cross product of 1, 2, dot, 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 n sets, which means that your cardinality, or the total number of lists, so total lists, would simply be the cardinality of that cross product, dot, dot, dot. That's done being n, which is the cardinality of those individual guys. And that's where each of these k's come from, because if the k1 through kn is the cardinality of the individual sets, that's just a shorthand way of saying this property. Okay? So that's the official tie-in. Now, that being said, if you want to completely ignore cross products this entire time, you can. You can still get through everything. The thing to remember is you find each of the individual objects, or how many objects could be selected for each of your individual positions, and multiply all those guys together. Okay. Now, it turns out there is a second principle, and this one isn't in your book, but it is a common property. If it had a name, it'd be called the addition principle. So for this one, it was late last night when I typed up the addition principle, and I had a total brain freeze on an awesome way to write it. So this is a very much description of what you would do as opposed to an awesome way of writing it. So for this one, if you have all of your lists, and it's just difficult to do what you're doing up here with the multiplication principle maybe, or maybe you just didn't think about the multiplication principle. If you can actually cut up those lists or divide those lists into several different cases. So like case 1, you do whatever you do. Case 2, then you get the next set of those lists, case 3, etc. Once you count up the total number of lists in each of the different cases, and maybe inside of each of these cases, you go back to this multiplication principle. That's pretty common. Once you figure out how many lists are in each one of those cases, you then add them all together to get the total number of lists. The key thing with cases is that you're not allowed to have one list in 2 different cases. So this is literally, you take like the entire list, the entire set of all your lists. So the example would be like if that's a list, 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 if that's a list. You break it up so you're looking at only some of the lists at a time. And then once you find the number in each of those sort of subsets, then you add the total number of lists in all the subsets together to get the actual total number of lists. Okay. these two principles here, the multiplication principle and the addition principle, if those are the only two things that you remember for this section, there will be more. We'll give you proper symbols and all that stuff. But if these are the only two things that you remember for this section, you'll still be able to solve all the questions, okay? Unless it actually says, what does this symbol mean, okay? So let us now look at some additional questions. But before I move on to the next question, do you guys have any questions so far on the material we've covered? All right, I don't see any questions coming in, so let us move on to the next example. Although if you do have questions, definitely shout them out throughout the thing, or I guess type them up. So the next example that we have is this guy. This is a classic example, and we'll describe what all these things mean. So the question here is, how many 5-letter words can be formed using the letters A, B, and C? And we are going to have to repeat letters if we want to actually build a 5-letter word. Now, the word words is actually in quotes here because we're not talking about dictionary words. We're really just saying we want to build a length 5 string with the letters. So this word is just, you could have inserted this with the word string. In other words, this is a perfectly acceptable word. But you could also maybe have only one A and maybe a B, maybe 2 B's, and maybe 2 C's. Now, question before we get going and counting is that last word, as I attempt to put little quotes in the way I speak it, and I realize that didn't really work very well. If we say we rearrange these letters, so maybe we have B, then A, then C, then a second C, then B. Notice it's the same 1A, 2 B's, and 2 C's. Are those last two strings, or those last two, in quotes, words, are they going to be counted as the same word or as two different words? What do you think? Would these two guys be counted as the same word or as two different words? Correct. And this is why it's common in this intro counting section to use the word words here to give you in your head this idea of, if I rearrange the letter in the quote-unquote word, you're going to get a new quote-unquote word, okay? So here, since we are dealing with a little finite string, if you scramble the order of the elements, it will give you a different word or a different little string. Now, that being said, let us see if we can't find out how many different 5-letter words we have with these criteria. Now, could we actually try to go ahead and write them all out? Sure, but let's not. If we need that, we'll let a computer do it for us. Okay? Instead, let's do that shortcut method that we did on the last example. So 5 letters, so we need letter 1, letter 2, letter 3, letter 4, and letter 5. This would be letter 1, letter 2. I'm going to do L3, L4, and L5 for the last one because I didn't write my little placeholder things wide enough for the word letter and a number. Now, in the first one, what can we have? We could put in an A, a B, or a C. Now, what options do we have for our second letter? Do we have the same options or do we have different options in terms of which letters we're allowed to use? Do we still get to use A, B, and C for that second position? What do you guys think? Can we still use A, B, and C, any of them that we want to, in that second letter position? Yeah, totally fine to do it. Is it cool to use those same? Why are you doing this? I didn't touch any button. Is it still okay to use A, B, and C for any of the next 3 positions? So for the letter 3, letter 4, and letter 5 in our word, still okay to use the same options? And the answer is yes, and I'm just slow to write it. All right, which means what can we do? In that very first position, we have 3 options. In the second position, we still have 3 options. In the third position, we have 3 options. In the fourth position, we have 3 options. And in the fifth position, we have 3 options. Or we simply have to figure out what 3 to the 5th is. So if we go ahead and we do the little bit of arithmetic, figuring out what 3 to the power 5 is, that should be 243, which means our actual answer here is, with those specifications given, there are 443 words possible, or possible words is probably the better way to say it grammatically. Okay. Makes sense? Questions? Still kind of feeling okay? All right, well, I'm not seeing any questions come in, so let us look at the next example. And the next example is actually what I'm going to throw to you guys. This guy right now is up and active on Poll Everywhere. Just a second, let me share that screen with you. So you've got the URL. And I didn't even attempt to put this guy inside the PowerPoint just because it's not showing PowerPoint and inside of WebEx with Poll Everywhere is just one too many link for the system, apparently. Okay. So for this one here, it's the same question on either one of the 2 slides. So let me go ahead and get rid of sharing one of these 2 slides, one of these 2 things. That way the screen is a little bigger for you guys. So the question here is, you've got a coin and you toss it 4 times. This notion of a fair coin just means when you toss it, it's going to land on either heads or tails, and it's not more likely to land on heads. It's not more likely to land on tails. You got a 50-50 shot each time of it landing on heads or tails. Okay. So the coin is tossed 4 times. Each of those 4 times you record whether the coin landed on its head or its tail, and that recording gives you your list. So your list is going to comprise of heads and tails. Okay? So the question here is, how many different outcomes are possible? In other words, how many different lists dealing with heads and tails are possible? And the assumption here is if your coin actually did land on its edge, you went ahead and like blew it over or put your hand on it and made sure it only turned up heads or tails. Okay. And once you guys have your guesses in, we'll go back and look at what to do here. So it looks like almost everybody has a guess. Only, one more person and it'll be everybody with a guess. All right, I'm going to go ahead and share the other screen that still has the exact same question on it. This question is still going to be active up in Poll Everywhere. It's just not going to be shared so you can see it. All right, so going back to this guy right here, and since I started writing and it switched me over to a black ink, I'm just going to keep it down like here, like this for just a sec. So I wrote out an example. So here, in terms of what you're doing when you toss it 4 times, each time you have the option of it landing either on a head or a tail. So I just wanted to write out a couple of options. One of the options is it landed on heads 3 times and tail 1 time. Maybe it was 2 and 2, so maybe you had a head. Maybe it then landed on a tail, a second tail, and then a head. Maybe you had 3 tails and a head, so maybe it was tail, 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 head. And then maybe it was all heads or all tails. So if it was all heads, heads all times, and maybe it was tails all times. Okay. So those are some options of what could have come up. Now, if you wanted to do this count without writing down all of them, and this is actually a small enough example, you could have written down all the possibilities. What do we have? Well, we've got for toss 1, so here's toss 1. Then we've got toss 2. Then we've got toss 3. And how many possibilities were there for toss 1, toss 2, or toss 3? How many options did you have? How many possibilities for each of these tosses? Yeah, for each toss, you could have an option of either heads or tails. So because there was the option of either heads or tails for each toss, you had 2 possibilities, the head or the tail. And that was the same for each of these 4 tosses, so we had 2 options all the way down. Now, putting that all together, that gives you a grand total of 2 to the 4th, or if you actually wrote that out, hopefully you were all thinking, hey, we actually have 16, that's so trying to be a 6, 16 different little options right here. And notice 16 is a small enough number that you could actually, you could actually have done that one by hand. Even if you didn't do this work right here, you could have written all of them out if you wanted to. Questions make sense? Kind of feeling okay? I am going to assume yes. So if we go to our next question, let me make this screen a little bit bigger. Our next question says, how many ways are there to arrange, or the other word that is often used here, how many ways are there to permute the numbers 1 through 3? And we often are just using integers here. So even though I say numbers, this is why I wrote them out explicitly in the set, we're really looking at the integers 1 through 3. Okay? Now this one here is a little bit different. Notice it says how many ways are there to arrange or rearrange these different numbers. So if we attempted to do this same problem, let's going to change up just a hair. Now before we jump into working this problem together, see if you can guess what's going to go on. So this question is also up on poll everywhere. It's this exact same question right here. See if you guys can make a guess on what you might do here, and then we'll talk about it together. So I'm just going to jabber a little bit while you guys are making your guesses, in part so that there's not dead air, in part to give you a little bit of extra information. One of the things that we're going to do, because the actual formulas in all of these counting sections are really, really straightforward. I mean, I can give you all the formulas in less than 15 minutes and explain how to use them in less than 15 minutes, but we're probably going to take 3 days to go over it. Part of it is wording, and to watch out for what are the buzzwords in the way that these questions are worded, and how to know which of the different formulas, once we get to formulas, how to know which of the different formulas to use. Counting counting topics do have a tendency to tend to mess with people's heads, not because any of the math is difficult, not because any of the formulas are difficult. Typically, everybody does perfectly fine with all of that part. It's figuring out how to read the questions and figuring out how to determine which of the techniques to use. So one of the big things that we're going to be doing in this section is I'm going to be throwing a number of these questions to you guys so you get more hands-on experience while we're still talking together before you get it all on your own. That way you don't get overwhelmed, and that way also I can show you the grand scheme of different ways that things are worded. Okay. All right, it looks like a majority of you do have a guess, but it's not as many as before. So let me wait just a hair longer for some more guesses to come in, and then we'll start talking about this guy. Well, part of this I can start talking about right now. Anybody have a guess on how long these lists that we're going to build for this question is going to be? In other words, how many positions are we going to have to deal with? For those of you who have already answered, or maybe those of you who are still working, any guesses how long the lists are that we're going to be building for this question? Or if you prefer positions, how many positions we're going to have to worry about? Well, I've got in a guess, and that is correct. So what we're doing here, one of the buzzwords in this question is the word arrange. And arrange means you have to use all. So use all the elements. Now it also means something else. Any guesses what that other thing is? So we're going to have to use all the numbers 1 through 3, or all the integers 1 through 3, but we're also going to have to what? Any guesses if we're going to be able to duplicate or repeat these guys? In other words, do you think we're going to be able to use the numbers 1 through 3 more than once? So there's always two options with counting. You can use your objects exactly once. For example, if you have people and you wanted to line your people up into a line, okay, that would be making a list of people. Could one person stand in 2 places in the line? No, it's impossible. Even if they're twins, they're 2 different people. Okay? However, all the examples we've had so far, or prior to this one, you were able to use the same object more than once, like when we were building our fake words. Okay? Why? Because you could use the letter A more than once. It was perfectly fine to have a copy. Now with integers, you can totally write integers more than once. The question is, are we allowed to do that when you're asked to arrange or rearrange these numbers? And that right there is totally the key thing. It turns out the buzzword arrange or permute tells us to use each of those numbers exactly once. So you put that together, or at most once. So when you put that together, what happens? So if we look at some examples, you could be super lazy and just say 1, 2, 3 for our list. You could be less lazy and say 1, 3, 2. You could be perhaps a little bit more lazy again and say 2, 1, 3. Is there any other list or 3-digit string that we could build starting with the number 2? So again, not the question that you were asked, but yep. So we could write out 2, 3, 1. We could also start with the number 3. What are some options if we wanted to start with the number 3? Yep, you could say 3, 2, 1. And you could also say what? Yep, 3, 1, 2. Okay. So those are some options. Now the question, of course, is, are these the only ways to rearrange the numbers 1, 2, 3? What do you think? Is there any other way to rearrange the numbers 1, 2, 3, where you're using each of these numbers exactly once? What do you think? Could we add in any extra little 3-digit numbers here to the end? Okay, there's only 2 possibilities for the answer, yes or no. We can either add in extra numbers, and if so, see if you can find one. And if not, we just won't. Yep. So it turns out there actually isn't any other ways, any extra ways to rearrange the numbers 1, 2, 3. We actually did it very strategically here, or methodically here. We started with a 1. There's only 2 ways to write a 2 or 3. 2 first or 3 first, and then we did the same thing starting with each of these numbers. So this was very similar to when we built our ordered pairs for the first example. Now, if we didn't write out all of those guys, which is totally fine, we also could have written out the count, so total number, which should be 6 if we do it correctly, where we actually do the same placeholder thing that we did before. Now, in the very first slot, what could happen? We could pick any of these 3 numbers, 1, 2, or 3, so that means we have 3 options. But in the second slot, or the second position, how many options do we have now? Do we still have available to us all three of those integers 1 through 3? In other words, how many options are we allowed to put in that second slot? Well, remember the key thing with rearranging things, or the other buzzword is to permute. What happens? You're only allowed to use each object exactly once. Okay? So in the first slot, you could have used any of the original 3 objects, but you grab one, you use it, you put it in the first slot. Once you've used one of the objects from your set, how many objects are remaining that you're allowed to use in that second slot? Yeah, so there would be 2 objects left that we could use. So this is our 3 objects from the original set. Subtract the 1 object that we already used. Now, using that same logic, how many objects are available for us to use in the third slot? Only 1, and that's the last guy standing. So here, once we have this new count, or this number of objects, that we had to decrease each time because we kept using somebody from the set and you weren't allowed to put it back to have it be available for the next objects, you multiply them all together, and when you multiply this guy all together, you will get a 6. And notice, 6 is exactly the same number of these rearrangements that we got up here at the top. Now, to just give you a little bit of terminology, so I'll go ahead and do terminology over here to the side. These guys up at the top, the actual 3-digit numbers, those guys are called permutations. And that is a buzzword. It's one of the reasons why the other way to say arrange or rearrange is also to permute. It comes back to this guy. And down here, that 6, there's actually something called a factorial. If you've taken Calc 2, and I can't remember how many of you guys said that you have taken Calc 2, you would have seen this before. If you've taken a stats class, you would have seen it before as well. If you haven't, don't worry about it. They totally borrow it from the counting techniques that we have. Officially, this is inside the subfield of discrete math called combinatorics. Okay? So a factorial, it symbolically looks like an exclamation point after an integer. Okay? So here's how it works. 3 factorial is you take the 3 and then multiply by 2, multiply by 1. In other words, it's 6. If you take 4 factorial, it's 4 times 3 times 2 times 1. So if you multiply all those together, it'd be 6 times the extra 4, so that would be 24. And I'm going to stop at 5 factorial because we should be able to see a pattern. 5 factorial is 5 times 4 times 3 times 2 times 1. Or if you multiply the 24 together by the 5, that would be 120. Now there are some special cases, and we'll look at the special cases in just a second. But in general, anybody have a guess for what the formula is for n factorial? Did you spot a pattern, in other words? You'd start off with that. So the pattern for the factorial is, it's going to be what? It turns out the official definition for n factorial is the number of ways to permute n objects. So that's the official definition. Number of ways to permute n objects. Okay? So you'll have n, and then you used 1. So then you'll have n minus 1, but then you use 2, so you have n minus 2, and you keep going all the way until you get to the very last object. Now, that works anytime you have a positive integer. So n equals 1, n equals 2, n equals 3, 4, 5, n equals 10. Okay? But there is a special case, and let me go ahead and write down 1 factorial, which is not a special case, and then the special case, which is 0 factorial. Okay. So I'll star the 2. If you only memorize those two, those are the 2 you need to worry about. So first, let's do 1 factorial. Any guesses what 1 factorial would equal? Remember, it's the number of ways to rearrange one object. Yeah, it would just be 1. That is not a special case. You plug it into the formula, you start with n, you got to 1, you're done. Okay? One of the ways to remember this is all the integers 1 through n, multiply them together. Keyword there is all of the integers 1 through n multiplied together. Now, when you get down here to 0 factorial, it turns out 0 factorial doesn't work with this formula because n, i.e. 0, isn't 1 or bigger. It's actually smaller than 1. So this is where you actually have to go back to the official definition of the factorial, which is the number of ways to rearrange n objects. Now, what happens if you have 0 objects? How many ways can you arrange 0 objects? So one of the ways that people talk about this is they think of like a table or a desk. If you place your objects on top of that table or that desk, if you have one object, you just set it down. Actually, I need to do this because I can't figure out how to do it without my hands. Okay, so you have your object, your table. If you have 2 objects, you can sit them both on the table, and there's one way to permute them, one way to set them down, or there's also a second way of setting them down. Okay, if you only have 1 object, well, here's your table, and it only sits on there 1 time. But if you have 0 objects, you still have the table. So if you try to guess how many ways to rearrange 0 objects, well, it turns out it's highly, highly related to the empty set. The answer turns out to be 1, which is not necessarily what you would have guessed. Okay, so what is this saying? How many ways are there to permute the 0 objects? Well, 1, because it's like having an empty table. There's nothing there. There's no way to rearrange it. You've only had that one way of literally seeing nothing. So that's the special case in dealing with these factorials. It has a tendency to not come up naturally in one of these type of examples. 0 factorial typically comes up when we start getting into our formulas, which based on the current time is probably going to happen at the beginning of next time. Okay. But that would be the idea if you have the buzzwords arrange or permute. Questions so far? Kind of feeling okay-ish so far. All right, so let us look at another example. Now this next example now put stuff into context. So a lot of times in counting questions you have context. So it's something that you might actually see if you walked around in the world. Sometimes it's not at all. Like the last example, it's something that we would see in math or in something that you need to code, but not necessarily something that you just randomly see out in the world. I guess maybe if you were printing signs and you only had numbers that you could put up onto a sign. I don't know. Anyway, so this next example has more context than the last examples. So here you've got some club, maybe it's a student club like what we would have at the university, and suppose it has 10 members, and for whatever reason they decide they want to pick officers. If it's something like our student clubs, is because they need to get registered. Okay? So assuming that no one is allowed to hold more than one of those 4 positions, the question is, how many different ways are there for that club to go ahead and select officers for those 4 positions? Okay? Now, just like with the last questions, I went ahead and threw this one to you guys up on the poll everywhere. See if you have a guess for what might happen. Okay? And so I'm going to go ahead and share this second screen with you guys. And let me stop sharing the current one just so that it is larger for you guys to see. Now this one is going to take a little bit more thought just because the numbers there are already combined together. So definitely build your formula first and then combine your numbers together. All right, so looking at this question, and we'll make this bigger for us. I went ahead and while you guys were working on the question, I did a little bit of blocking. Okay, so I did a little bit of scratch work for us, a little bit of placeholding. Any guesses why I would have put the office positions here of the president, vice president, secretary, and treasurer, as opposed to the 10 slots for 10 different members? Any guesses why I chose these ones as opposed to 10 of them, besides the fact 4 is easier to do than 10? Because that's actually not a consideration in these questions, sadly enough. Ooh, close. So it turns out if you're trying to figure out who's going to be each one of these slots, suppose you're looking at specifically maybe treasurer. Who's going to go to be the treasurer? What do you have? The options for the people that could potentially be treasurer are those 10 members of the club. So in terms of the list that you're building, you're actually building the list of the names of the club members who would be in these different positions, these office positions. Yes. So this first position, and order it however you want. I did the same order here that was inside the parentheses, so president, VP, secretary, and treasurer, just because having served on way too many student clubs back when I was a student, that's typically how you would see it if you saw a ballot. Yes, you would have 10 options in the first position because any 10 of the members could be there. Then for VP, since they're not allowed to double up in terms of which positions they hold, then you'd have 9. For secretary, then you'd have 8. Now, what you typed in only went down to 8, so anybody have a guess on what we should do for the next slot? Yep, you guys totally nailed it. So the next slot right there would totally be 7, and then what would you do? You would then multiply it, and actually let me put the multiplication slot down there, and just like on the last example, I'll go ahead and give you some of the notation over here on the side. Okay. So then you just oh please come. Then we would multiply these guys together, and if you multiply those guys together, I'm totally going to cheat and write down what I plugged into a calculator earlier. So this turns out to be 5,040 different possible ways that you could vote in or make those people go and fill the offices, whether it was something they wanted to do or they got guilt-tripped into it, okay, depending on how the club was. All right, so that would be dealing with this guy. Now, as some of you have noticed, this guy looks really, really similar to who? It looks really, really similar to that factorial thing that we looked at just a little bit ago, this one here, except the definition of a factorial is you multiply all of the integers n, wherever you started at, all the way down to 1. Did we multiply all of the integers 10 to 1 together? In other words, did we go all the way down to 1? And the answer, of course, is no, as several of you have typed in. So this is actually this is not the official word. I'm going to give you the official word in just a second. But this is essentially a truncated factorial. In other words, you stopped before you got all of the terms for a factorial. It is called something different. And the thing it is actually called is a falling factorial. So falling factorial. In terms of symbols, it looks like this. N, and the parentheses are needed. It's actually part of the symbol. And then there's a subscript with a K. Now here's what it all means. The N inside the parentheses is like the factorial N. You start there, and then you multiply by the next number smaller, and you keep going until you get to an ending part. The K right here tells you how many total terms you're going to have out of your factorial. So you're going to have a total of K terms, which means in this last term, that's going to be n minus, and everybody wants to say k, n minus k, but it's actually not, Notice the second term here is n minus 1. So this first term is like n minus 0. So the count's 1 off. So first term is n minus 0. Second term is n minus 1. So kth term is going to be n minus k minus 1, which means if you actually write it out, it would be n minus k plus 1. I don't care if you remember that last term. I actually didn't even remember that last term until I had to start to teach it. The thing to remember is you start at n and you go out k terms until you stop. Okay. Now, this is also, as a couple of you noticed, the same thing as a factorial. And if you need only k terms, well, you have a remaining n minus k terms that you don't need, and this division right here deletes off those extra terms at the end that you didn't want. Okay? So that is another way to write this out. Personally, in terms of what we're doing here, I would recommend learning it like this or remembering it like this, but if you already know the following factorial in the other sense, you can do it right here. This guy is also symbolically, if you've ever seen it, the other symbol for it is a little teeny tiny n, capital P, and then a little teeny tiny k. The P there stands for permutation, okay? Except it's not quite the same as the factorial, so they did a P there instead. Okay? So if we go back over to our example we had with the club, this guy here would be exactly the same as, in symbols, 10, and the subscript here would be 4. Okay? So that would be the symbols attached to this question. Questions make sense? Kind of feeling a little bit okay. So the next thing we have is the activity 6. So the questions for you guys to work together in a group. But before I throw you in there, I want to make sure that I answer any questions that you guys have. So any last minute questions that you guys have before we start jumping into group work? All right, I am not seeing any questions come from you guys. So I'm going to pull up what the activity is. Share, and I need to stop sharing that other one. There we go. So this one here is our activity 6. It doesn't actually have an activity 6 on the name up there, but it actually has, and here's the thing that I want to make sure to mention to you guys, it has 2 pages. Okay? The first page starts off and says, hey, try building an ID code for some company, and it gives you a bunch of different specifications, and it's got 2 parts. The first one is if it's written exactly like this, and the second one is what happens if you change up the requirements just a little bit. On the second page, you've got 3 questions. The first one deals with area codes of phones. The second one deals with putting books on a bookshelf. And the third one deals with people sitting in a circle. If you want to, feel free of thinking about this as people sitting around a round table. That's what it's often described as. Or various ways you can think of people being in a circle for whatever reason. Okay? Try to get through at least the first, I would say at least the first 3 questions in the next little while, and then we'll come back and talk about them with any questions that you guys have. I'm going to give you guys about 15 to 20 minutes. At 15 to 20 minutes, you're probably not going to get to the last question unless you guys know exactly what's going on and are super speedy. Okay? All right. So I didn't see any questions come in while I was talking about that, so I'm just going to go ahead and throw you guys into your groups that have already been randomly selected. Okay? So here we go. 3, 2, 1. I'm sending you into groups. Patchwork. All right. So first 2 positions were allowed to be any 2 capital letters. Next 3 positions were any digits, 0 through 9, and the last position was either 0 or 1. And the difference here of 1B versus 1A was you couldn't repeat anything. So in this first position, how many different possibilities were there for your first letter? Don't overthink it. Although, typos do happen here. So it's just what? You count up how many letters are from A to Z, and hopefully you all got the same number of 26. Now, once you used one of those letters in that first position, how many possibilities did you have for the second position? Don't all speak at once. Yeah, so you had one fewer, so now you had 25. And that takes care of it for the letters. There is no more, okay? That's it. You're done with the letters. Now, when you look at the next four characters, all four of the next four characters are going to be digits, somewhere 0 through 9, although the last one's only allowed to be 0 or 1. So what happens? You can pick one digit here, then that one can't be used over here, then the one here can't be used over here, so it's going to look like a factorial or really a falling factorial, okay? But did anybody run into the sort of trick or the issue with 1b? What was the problem with 1b that you had to pay attention to? Did anybody notice what that issue was? It's not really an issue, but it's a quirk you have to worry about. It's only with the digits, not the letters. So for example, suppose you start building a string, one of these ID codes, and you say AB because you're lazy. And then the next letter is 1, 0, 1, 2, and then what do you put for the last digit? Or how would we put in that last digit? Well, that last digit is supposed to only be 0 or 1, but you weren't allowed to repeat digits. So what's the issue here? If you're only allowed to put in 0 or 1, and both of them have already been used, what does that tell you? That tells you, oh dear, there's a problem. Well, there's a bunch of different ways to fix this. One of the ways is to break it up into two cases. Case 1, your last digit is 0. Case 2, your last digit is 1, and count it from there. Or you can be sneaky. Anybody feel like being sneaky? I'm going to assume all your answers were yes. So if you're being sneaky, it turns out here what? You're multiplying stuff, right? Well, when you multiply stuff, it doesn't matter what order you multiply the numbers together as long as you got all the numbers, right? So first of all, start at the end here. So if you start at the end, how many options you have? You can pick either a 0 or a 1. It doesn't matter which one. So that's 2 options. Now, once you select that 2 options, you've either picked a 0 or 1, so that's 1 fewer from the 10 digits that you were allowed over here. Now, you don't know if it's 0, you don't know if it's 1. So if you pick 0, your selection now would be just the digits 1 through 9 in those 3 slots. If you had picked a 1 for the last position, your possibilities for those middle 3 slots would be 0 or then 2 through 9. Okay? Either way, what happens? We have 1 fewer. So that means for these slots, instead of having 10, you have 9, and then 8, and then 7. So notice it's that same sort of factorial or really falling factorial issue here. And you can rearrange it, make 9, 8, 7 is totally fine. But notice instead of starting with all 10 of your digits, you pulled out the one of them that actually got used back here first. Now, that's not the only way you can do it, but that is a way to do it. And we actually are past time, so we'll go ahead and stop right there. If you guys want me to go over some of these other ones, we can do that at the beginning of next time. Okay.